Okay, we're going to go over types of chemical bonds and talk about the different types and how the forces between the atoms actually determine the type of bond. We all know the bond is a force that holds atoms together and makes them function as a unit, as a molecule. Bond energy can differ between the atoms. And the bond energy is the energy required to break a chemical bond. Okay, so talking about bonds, there's different types. One type we may have already heard about, that's the ionic bonding. It's where two ions are bonded together. Generally, a electron has transferred. So one is very electron greedy, that's the non-metal, and it usually bonds with a metal that could handle giving up its electron and is happier having a shell that's not got empty parts to it, right? We don't want empty valence shells. So that metal is really close to just losing one, two, or three, and then its outer shell is no longer partially full, right? We don't want anything partially full. And that usually works. A metal plus a non-metal makes an ionic compound. They sit next to each other when they're solid, and they kind of actually stack in a crystalline structure, so they can be very beautiful with a cation and an anion, but you can see that they're surrounded, all the anions are surrounded by cations and stuff like that. So what we do when we write the formula, we say one cation and one anion because that's the ratio of cations to anions. And when you put ionic compounds in water, they like to dissociate. And so they actually wander apart because the chemistry of water, water is a polar molecule, and we'll talk about why that happens. Okay, so ionic bonds, an electron is transferred. So the atoms are no longer neutral and they're called ions. Covalent bond is a different kind of bond where electrons are shared, and it's a stronger bond because atoms have to be near each other in order for them to share electrons, right? So atoms can be shared at different amounts. In the case of hydrogen, hydrogen can bond with another hydrogen. Since hydrogen wants one electron, its one electron that it has can be shared with a second hydrogen, and then that second hydrogen can share its electron with the first. So they both feel like they have two electrons. They both feel like they have a full outer valence shell. Remember, hydrogen and helium, they only have electrons in that first orbital that only holds two electrons. So they are happy with two total. So hydrogen will feel like he has two. We denote that bond by like a line, but you have to kind of think of it in your mind that the line has an electron at one end and an electron on the other. In this case, only one electron is shared with one and the other one is shared with the other. We call that a single bond. And since hydrogen both have similar chemical characteristics, they share that electron evenly. So here they are, supposed to be a representation of the electron clouds sort of mingling. And even though electrons, don't stay in the same place, they are shared rather evenly. So that's a covalent bond that's evenly shared exactly. And we have a name for that, all right? Here's a type of bonding, though, that occurs between two atoms that like electrons at different amounts. As you can see at the bottom, the fluorine has a negative sign next to it. It's really more partially negative because it's greedy for electrons. It wants electrons more than hydrogen does. Hydrogen still wants its electron, but just not as much. So it's an uneven sharing. So that electron's going to spend more time around the fluorine, that electron that's shared from the hydrogen, and less time around the hydrogen. So that gives the hydrogen less than neutral charge, right? So normally hydrogen has one proton and one electron, but if it only has an electron some of the time, then it's more positive more of the time. And since fluorine it has a bunch of electrons, but it's got an extra electron, one more than its number of protons, then it's going to be a little bit negative. So we say partially positive, partially negative, and we use a sigma to kind of denote that it's not a transfer of an electron. The hydrogen didn't completely give up its electron, and fluorine didn't completely take it, but it's just an uneven sharing, and we call this a polar ionic bond, right? It could be, this is a polar covalent bond. There we go. There we go. So we actually have a scale to tell us how badly an atom wants an electron, and that helps to determine whether this is going to be a regular non-polar covalent bond or if it's going to be a polar covalent bond. All right, so electrons shared unequally. Well, we won't know that until we know how badly each atom wants an electron. So here's this scale of electronegativities on the periodic table. And you can see fluorine is in the upper right. It's a smaller atom, and therefore it wants to have its electrons real bad. Okay, that's the trend. So lithium over here, remember he could lose an electron and be very happy. So it still has protons in its nucleus. It's still going to crave electrons, but just not as much, right? It's scale of 1.0. If the scale goes from 0 to 4, lithium's about a 1.0 in electronegativity. Okay, so the scale of electronegativity increases as you go from left to right because you're gaining more protons in the nucleus, and of course the size is going to decrease because those electrons that occupy that electron cloud are going to get hugged closer so that the atom gets smaller. Also, those electrons are going to be closer to the nucleus. They're going to be harder to pull apart. So there's more protons to pull those electrons in. They want their electrons more. Electrons are harder to yank off, just like you're harder to kidnap if you're closer to your parents, right? Okay, so that's why it would increase from left to right. Now, as you go down the periodic table, there's, bigger atoms. We talked about that because you're adding shells. Each row you go down the periodic table, now you have more shells for those electrons to occupy, and they get that much farther than from the nucleus. So those outer electrons are going to be easier to pull apart. They're farther from the nucleus. It's like if you're in a big group and you're far away from your mom or dad, you might be easier to kidnap. Okay. So that's why chlorine, and bromine and iodine, as you go down, have much less electronegativity than fluorine does. So you can understand it that way. You can also take a screenshot or print this off. You're going to want this chart for things that we do later in calculations. You got to be able to calculate electronegativity, how different in how each electronegativities of the two atoms are. How different are they? That'll determine what type of bond. Okay, so if we're comparing lithium and fluorine, they react, which has more of an attraction with an electron? Okay, so we just saw it. Lithium was 1.0, fluorine was 4.0. Fluorine is going to be more electronegative. Why? We talked about that. Electrons are the same distance from the nucleus, but fluorine has more protons. Okay. And if you took fluorine and iodine, remember iodine was the one that was below, so it's several or a few levels more for the electrons to occupy. Yeah, fluorine is a higher number. It's going to attract the electrons more. We're going to want electrons more, or it's going to hang on to its electrons more than iodine. And iodine, if it gets close to electrons, of course, iodine's got a large electron cloud. The nucleus of the iodine can't even get close enough to other electrons to really pull on them hard. Kind of like magnets. When you put magnets real close to each other, they have a real attraction to each other. If they're a lot farther apart, you can virtually hardly sense any attraction at all. Okay, so I'd say, yeah, iodine has more shells for the electrons, so the outer electrons are farther from the nucleus. Okay, so the trend for electronegativity, what's that? Well, as your atom gets smaller, electronegativity should increase. That's one way to put it. As you go down the rows from left to right, electronegativity should increase because you have more protons and proportionally to the number of electron shells. And as you go down the periodic table, down the column, you're adding shells, so you're going to decrease in electronegativity, or the less electron shells you have, the greater the electronegativity. So those are some ways to describe that. Okay, but we're going to talk about the difference in electronegativity and how that affects the polarity of the bond between two atoms. Okay, so we talked about the first situation where it's going to be even sharing. You can see that electron cloud looks pretty even. We're going to call that a non-polar covalent. Okay, so electrons are shared pretty evenly. That's going to mean, in all practicality, the electronegativities are less than 0.5 in the difference. If you go back to our little periodic table over here, they would have to be pretty evenly matched to do that. Maybe boron and carbon, all right, or maybe carbon and nitrogen. Okay, that's fairly non-polar non-polar covalent, because electronegativities are pretty close to each other. Polar covalent is where you're going to have an electronegativity difference between 0.5 and 1.7. All right, so close to that. So I guess maybe carbon and nitrogen, those are pretty close to being a polar covalent compound. Okay, I'll buy that. But maybe hydrogen and carbon, that's a 0.4 electronegativity. That could be a non-polar covalent. Okay, so scratch that. We decided between boron and carbon, let's call it a polar covalent. And between carbon and nitrogen, it's still covalent, but it'll be a polar covalent compound. Okay, so there's various scales on these, but to completely transfer an electron and become a polar bond, cation and anion, and become an ionic bond, is another way of saying that, the difference has to be greater than 1.7. And that makes sense because you have non-metals over here, or not metals over here, and they're pretty low in electronegativity. And then you have some non-metals over here, and they're pretty high in electronegativity. Okay, so those differences are going to be greater than 1.7 usually. So our rules still worked, but now we know kind of more specifically what type of bond it is and how to calculate it. Okay, so here's a chart just to kind of compare. Hydrogen, hydrogen, they have the same electronegativity, so obviously the difference would be 0, definitely covalent. Let's see, electronegativities of sulfur and hydrogen are going to be about 0.4, so we're going to, some people call that a polar covalent. Yeah, I don't know. I'd say on our scale, we called it a non-polar covalent, didn't we? Because that was 0.4. So yeah, let's just call that one a non-polar covalent. So there we go. All right, so chlorine and hydrogen, they have a difference of 0.9. That's going to be in the polar covalent range. That's greater than 0.4. And then oxygen and hydrogen, that difference is going to be 1.4. Still polar covalent. But fluorine and hydrogen, so this one's a weird one. It's 1.9 and it's greater than 1.7. So you're like, wait, I thought that was supposed to be polar. Ionic. I guess fluorine and hydrogen is just that one exception where their bond still acts like a little covalent and not really ionic. It still acts polar covalent. So we'll let them call this polar covalent. But in my class, if you put down that as ionic, I will not mark you wrong, because yes. All right, arrange the following bonds from most polar to least polar. Okay, so what you need to do is look at the chart, calculate the differences, right? So we've got to look up nitrogen negativity, right? 3.0. Fluorine, you don't have to worry about whether it becomes a negative difference or a positive difference in this case. We're going to say difference of 1.0. Right? Oxygen and fluorine, that's going to be still 4.0 for fluorine, okay, but 3.5 for oxygen this time. Yeah, fluorine gets a 4.0, and that's a difference of 0.5, right? Okay. Carbon and fluorine, we got to do 2.5 minus 4.0. Right, that's a 1.5 difference, right? So as between oxygen and fluorine, if they bonded, that would be a non-polar. That'd be a polar covalent, right? Yeah, because it's greater than 0.4. Same with nitrogen and fluorine, and same with carbon and fluorine, because they're all less than 1.7 but greater than 0.4. Okay, so that's interesting. Most polar then least polar. Oh yeah, most polar would have the greater difference, right? So it's carbon and fluorine. That's the most. The middle one will be nitrogen and fluorine, and then the least will be oxygen and fluorine. Okay. Yeah, we hit it. Nailed it. Okay. Now, the most polar to least polar, I think now we have comparing, like, not just compounds that are bound to fluorine. Okay, so carbon and fluorine, That's going to be 2.5 and 4.0. Those are the differences at the 1.5. Nitrogen and oxygen, that will be a 3.5 minus 3.0. Okay, so 3.0 for nitrogen, so that's 0.5. Silicon and fluorine, that's a 1.8 and a 4.0 difference. Okay, so that one's a 2.2, right? That's a lot. That's a pretty big difference. Okay. Which one is the most polar? Yeah, the biggest difference. Silicon and fluorine. Then comes carbon and fluorine. Then goes nitrogen and oxygen. The first two are carbon and fluorine and nitrogen and oxygen. Those look like they're going to be polar covalent compounds. Silicon and fluorine, that's above 1.7 by quite a stretch. So that one's going to actually end up being an ionic bond. Is going to be electron transfer. Okay, let's see how we did. Nice. Okay, so you could do that on your own. If you want to arrange the following bonds from most polar to least polar, you can pause the video. Look those up. How'd you do? There we go. Okay. Which of the following bonds would be considered the least polar, but still considered polar covalent? So anything that is a 0.4 difference or less is going to be not included in the polar covalent because it would be the non-polar. Okay, so if you look those up, maybe you want to pause the video and look these up. I can tell you right now, the oxygen, with oxygen, that's going to be 0 electronegativity. So don't even bother with that one. Okay. How did you do? I guess I gotta calculate this real fast. I don't have my slide calculated. All right, magnesium and oxygen. I'll let you do that on your own. We're gonna go to dipole moments. Are you having a dipole moment? You might. Okay, I hear you. What really is happening is they're just saying, like, what's the difference in polarity? Let's give it a name. We're going to call it a dipole moment. And it always has a place for a positive charge and a place for a negative charge. Okay, so great when you have two atom compound. Okay, so you can definitely tell the dipole moment, the electron direction is going towards the fluorine. It's more electronegative. It's partially electronegative there. Now, the thing is the molecule's got to be asymmetrical or linear, or at least in this case, or just have two atoms. Okay, I don't know how better way to say that. It's not completely asymmetrical. So let's look at water. So the difference in the dipole moment of hydrogen and oxygen, hydrogen's like 2.1, oxygen is 3.5. So let's give it a 1.4. Yeah, it's not an ionic compound, but it is an uneven electron sharing, right? It's a polar covalent compound. All right, so I'm just saying that this was going to be a polar compound because there's an asymmetry for it. So you can really put an arrow towards the negative charge, and that's towards the oxygen. Oxygen is going to be the partially negative because oxygen has these other, remember the structure of the valence electrons. Oxygen has these other electrons hanging out there, and they actually repel the hydrogen and keep the hydrogens on the other side because remember, hydrogen is a proton in it. So it's going to repel the proton. And hydrogen is less electronegative. So the electron's going to spend less time around the hydrogens than they are the oxygens. So there is a direction to it. There's a north pole and a south pole, right? There's a positive end and a negative end of this molecule. So the molecule is going to be polar. That is a different deal than whether or not the bond is going to be polar covalent or not. Okay. So yeah, this is water has a dipole moment, they call it, because it has a direction for its partially negative end in the molecule and has a partially positive end. And that's good because water then mixes and dissolves all kinds of ionic or polar other compounds like salt, NaCl. The sodium would be positive, and then the water just sticks its negative end towards the sodium. And then for the chlorine floating around, dissolved in the water just sticks its positive end closer to the negative or anion, right? By the way, this causes water to remain liquid at higher temperatures. Okay, there's other compounds that are similar to water, but they're not liquid at higher temperatures. They're a gas. They don't hang around each other as much. But water, since it has positive and negative ends, it loves itself. It's hydrophilic, right? So because it'll hang around itself. The negative oxygen will hang around the hydrogen of a different water molecule, and it'll stay together. That's why raindrops stay together when they're on your windshield, and why you can like overfill something. You can bubble over. Water has that surface tension because of the polarity of it, and then it has a dipole moment. Okay, is CO2 a polar molecule? Okay, between the carbon and the oxygen, the bonds are polar. Yeah, I'll tell you what. Carbon's a 2.5 electronegativity, and oxygen is a 3.5. So the difference is 1. We do have a difference in electronegativity, but as you can see, carbon and oxygen, they're all symmetrical. Like you couldn't put an arrow that goes, oh, this is the positive end, this is the negative end, because the arrows would be both pointing out from the carbon to the oxygen. So both oxygens are a little electronegative, a little electron greedy. But overall, it's a neutral molecule. It's not going to be polar. And it's why carbon doesn't sit next to each other very well. And it's easy to boil. It's a gas at room temperature, even though it's very similar in its construction to water molecules. Water molecules are polar, and then they're going to stick next to each other, and they're going to dissolve other things. Okay, thank you. I want you to practice calculating the difference in the electronegativities with atoms and finding out and figuring out, thinking about a molecule and if it's asymmetrical or not, or it has a dipole moment. So you have a certain defined direction to it, and then you'll know if the molecule itself is polar, even though it has polar covalent bonds in it. It may not be a polar molecule. All right. Thanks a lot. You guys are great. And hopefully we'll talk to you soon. Let me know if you have questions.